Hi guys, I'm recording this video for the upcoming Monday class, and then as I announced in the previous class, so we will not have classes. We will not have a class on Monday because the next week is the exam week, so I want give you some time for preparing for the midterm exam. Okay. So, and then the midterm exam will also cover chapter 3. So this is in chapter 3, we will, we will learn about the hardware components in a computer system. So, but you, you also need to study this chapter 3, the arithmetic for computers. But as I mentioned in the class, so actually this part was covered by the digital logic design course. So actually you can review it. And then, so actually for for hardware arithmetic units, so I briefly explain. So because this is some reviews, it's a kind of, this, these topics uh, were already covered by the digital logic design course. Okay, so so let's learn about some basic integer arithmetic units. So firstly, we can start from addition and subtraction. So how can you add two numbers to? So actually in the decimal number, so we can just add two numbers. But the computer system handles uh, digital numbers, right? It's a binary numbers. So actually like the decimal numbers, we can just perform the addition for each digit. So this is the example. So 7 plus 6. So 7 is the 000111, and then 6 is the 000110. So we can start from the LSB part, right? So if we just add the two numbers from this digit, then so it's 1, and then carry can be generated. So actually the carry is 0. So actually for the next digit, we need to add the three numbers. So two numbers plus carry. Okay, so this carry is called the carry in, and then carry is also, can be also generated. So for this digit, so so actually 1 plus 1 is 10, right? In binary. So carry the 1, the 1 is generated as a carry out, right? And then this carry needs to be included in the addition for this digit, right? So it's just very simple. Actually, we can implement the addition using full adder logic. Okay, so actually the full adder was covered in digital logic design course. Okay, and then actually, so this is the hardware. So hardware. So in the hardware, the hardware resources are limited, right? So, and then we are performing, so we are learning about the 32-bit computer systems, right? And then also we are learning about the RISC-V 32I, right? Right? So when we perform the addition using the add instruction, x1, add x1, x2, and x3, right? So these are register operands, right? And then what is the size of a single register? It's 32-bit. So which means when a RISC-V CPU execute add instruction, that it performs 32-bit data plus 32-bit. So what's the problem? If we just add two numbers, then the overflow can can be generated. So which means, so 32-bit, actually 32-bit plus 32-bit may generate the 33-bit number. But what's the problem? So actually the result is also stored in the destination register. So this, the size of the destination register is also 32-bit, right? So we cannot store 33 bits, right? So if Actually, so when the two numbers are added or subtracted, and then if the 33-bit numbers are generated, then this is called overflow, right? And then, so what's the problem of this overflow? So if overflow is generated, then the result, the result will be incorrect, right? So, which means a CPU needs to detect overflow, right? So for the addition, the overflow detection is very easy. It's very simple, right? We can just check the sign bit of the result. So for example, if we just add the two positive numbers, the result should be positive number. But if minus is detected, so it's a negative number is generated, then you can find the this is the overflow case, right? So if overflow is detected, so actually the result is wrong. So we cannot use this result. And then minus plus minus, it should be minus, but if the plus is detected, and then it is also overflow, right? And then if we just add the positive number and negative numbers, then no overflow. The overflow will not be created. Okay. And then subtraction. Actually, the subtraction is the addition. It's the same, right? It is because, so 7 plus minus 6 is so actually 7 minus 6. 7 minus 6 is equivalent to 7 plus minus 6. So actually, we can negate. So in order to perform the subtraction, we first negate the second operand, and then we can perform addition. So if you check the RISC-V instruction, then you can find that the RISC-V also has the sub and add. So add instruction performs addition, and sub instruction performs subtraction, right? But actually, we can implement the sub instruction using the adder, the addition hardware, right? So in chapter 4, okay, in chapter 4, we will learn about some hardware architecture, and then as you can find that, so actually in a lab design, so you can find that we can implement the subtractor using actually the existing adder, right? So subtraction is just the positive number plus negative number, right? We can just change the sign bit of this second operand, okay? The overflow can be also detected like the same way. So, okay, I will pass this one. So actually the adder and subtractor, this are simple and easy to understand. And then let's learn about the multiplication. So, so actually we are learning about the arithmetic unit. So arithmetic unit performs the arithmetic operations of binary data. But actually, the basic concept is the same. So for the decimal data, we can just also perform the arithmetic operations. Well, actually, so for example, the multiplication. So for the decimal data, we can just perform create the partial product, and then we can just add or generate the partial product, right? And then we can get the result of a multiplication. So it's the same. It's the same to the binary number, right? So this is the example of the multiplication. So multiplication is it's a C. So result to C is the A multiplied by B. So we can say that this is the multiplication. So in this equation, the A is the multiplicand, and then B is the multiplier. So multiplicand and the multiplier. The multiplicand is multiplied by multiplier, and then we can get the result. The result is called a product, right? Then how can you perform multiplication? So for each digit of multiplier, then we can perform the multiplication, right? And then we can generate the partial product for each digit, right? So this is called the partial product. So we can call it as PP, okay, partial product. So for each digit, we can generate the partial product, and then we can just add the all generated partial products, and we can get the final product number, right? So, and then also each digit of multiply has only two numbers, right? 0 and 1. And then, the one, if the multiplicand is the multiplied by 1, then the same number will be generated, and then multiplied by 0 is 0, right? And then we can just add the all partial product. So this operation can be implemented like this. So for each digit, of the multiplier, that we can generate the partial product. Okay, so this is the multiplicand, and then this is a multiplier shift right. So in the multiplicand, so and then by shifting the multiplier by right, then we can get the each digit, and then each digit is just multiplied by multiplicand, and then we can get the partial product. So partial product is also accumulated by this accumulator. Okay. So this is the multiplication. So it's the same to the decimal multiplication. So multiplication hardware can be implemented like this, right? But actually, this is very inefficient. So why? Because in order to generate for each partial product, then we need to shift the multiplier one by one. So in order to generate this partial product, then the multiplier is shifted by right by 0, and then 1, actually is by 1, and then by 1, and then we can generate this partial product, and then also shifted by 1, then we can also generate this partial product. So this is inefficient, right? Because we need to shift, right? so actually, uh, we can just implement the multiplier like this, right? So if we just implement the multiplier like this, then actually to every clock, then we can just shift the multiplier, and then we can get some each digit number of the multiplier. Then what's the problem? The problem is that in order to shift the multiplier by 1 for each cycle, then it is consume 32 cycles. Okay, so for example, if the RISC-V performs the multiplier instruction like mul, then like mul x1, x2, and x3, then what's the problem? The clock cycles for this mul instruction can be 32. So what's the problem? So when we learned about the performance, so it's the execution time of computer system, then what is the equation? Execution time, instruction count by CPI multiplied by TC. So for multiplication, it consumes 32 cycles. So CPI is 32 for multiplier, the multiplication, right? So what's the problem? Execution time is increased by this multiplication, okay? Multiplication instruction. So that's why we need to reduce the number of cycles for instructions, right? So for some complex instructions. So in this example, so we are learning about the arithmetic units. Then, so multiplications. The multiplications can be the examples of the complex instructions, right? Because a single instruction can consume the multiple cycles, right? So if the multiplication consumes a large number of cycles, then performance can be degraded. So we need to reduce the cycles for multiplication. So we implement the fast, fast multiplier, okay? That's the multiplier. And then it's very simple actually, because parallel operations can be possible for the multiplication. So for each digit, so we actually, in real world, we just generate the every partial product, but these partial products can be generated in parallel, right? That's possible, right? So this multiplicand can be multiplied by the many bits of the multiplier concurrently, right? And then these partial products are just accumulated using the adder tree. Okay, this is the example of a fast multiplier. So by doing this, so we can reduce the number of cycles for multiplication. Okay, but so as you can see, so but even though we use this fast multiplier, then this fast multiplier includes the many adders, right? So normally the multiplier consumes more cycles than adders, okay? Because the hardware is more complex, okay? So RISC-V supports the several instructions for multiplication. So more H, more HU, and more HSU, right? So problem is that if we just perform the 32-bit multiplied by 32-bit, then 64-bit product, 64-bit result will be generated. But what's the problem? The problem is that so we can just store only 32-bit data to the register. So what's the problem? If the number is very large, then actually the 64-bit, the more than 32-bit result will be generated. So then we need to also keep, we need to keep the upper bits of the result. So if we just use the mul, so it means the multiply, then it just stores the lower 32 bits of the product. And then if we use the mod h, then the more h stores the upper 32 bits of the product. Okay, and then more hu, and then you can find the more hu and then more hsu for the signed and unsigned numbers. Okay, so this is the multiplication. And how about the division? So division is the same. So like the decimal number division, so we can perform the binary number division. So, but when the division is performed, so A divided by B, then quotient is generated, and also the remainder is generated. For this is the integer division. No, it's not floating point division. So this is the integer division. So when the two numbers are performed for division, then the quotient can be generated. Also, the remainder is generated. Okay. So this is the example of the division. So the number A. So number A is divided by B. So this number A is called a dividend. Okay. It's a number to be divided. Okay. And then B divides number A, so B is called a divisor, okay? And then the result is Q is called the quotient, and then you can also get the remainder. It's the result of the modulo operation, right? So then how can we perform division? It's the same, right? How can you perform division in decimal number? So, right? It's the same. So we can first compare the, so we, for the division, we first start from this the MSB part. So most significant part. So we can start from this MSB 4 bits of the dividend, and then this dividend is divided by divisor. So how can you divide? How can you get the quotient for this part? So we just compare. So because this is the binary number, so it's actually the binary number, the Q, the bits of a bit of quotient can have only two values, 1 and 0, right? So what's the problem? So actually, in order to perform the division for this dividend between this dividend and divisor, then we can just compare, because on the quotient can the bit of a quotient can have only two values, 1 and 0. So if the dividend part, so this 4-bit is larger than the divisor, then quotient is 1. Otherwise, otherwise quotient is 0. So in this case, 1001 is larger than 1000. So the quotient bit of this digit is 1. And then we perform subtraction. Okay, 1001 minus 1000. Then this is 1. So for the next part, okay, this is the 0010. So what's the problem? 0010 is smaller than 10000, right? So this is 0. And then the next 101 is also smaller than 100. It's a 0. And then next part, the 1010, and then it's larger than 1000. So it's a 1. Okay, it's a minus 1000, and then we can get the remainder 10. Okay, so this is the division process. Okay, so but what's the problem? So division for each digit, division requires comparison. Okay, comparison. So how can you compare the size of two numbers? So we can compare the size of two numbers using subtraction, right? If the a minus b is larger than 0, then which means a is larger than b. Otherwise, a is less than b or equal to 0, right? Right? So for comparison, the division needs to perform the subtraction. But this subtraction is the conditional subtraction. So the problem is that if a is larger than b or equal, then we need to perform the a minus b, right? Otherwise, else it's just a. So this is the conditional operation. So division requires conditional operation like a minus b or a based on the comparison result, right? So that's why division is more complex than obviously adder and subtractor. Also, divider is more complex than multiplier. So as I mentioned, for the multiplier, parallel computations can be possible, but in the division, parallel computation is not usually possible because the result of the division is changed by the condition, like a minus b, right? So firstly, we can perform the a minus b, and then if a minus b is larger than 0 or equal to 0, then quotient becomes 1. Then a minus b is perform A. So actually this is the same result. Otherwise, it's a less than 0, then quotient becomes 0 and A is delivered to the next step. Okay, so this is how the division is performed in the hardware, okay? So like the multiplier, we can implement the divider like this. So we just shift the dividend. So we just compare the digit of dividend using the divisor. And then we perform the subtraction, and then the and then this operation is just repeated. Okay. So this is some optimized divider, but you can find that the architecture, the hardware architecture of this divider is just similar to the hardware architecture of a multiplier, right? But it's also very slow, so it will take multiple cycles. So which means that we can implement the best divider. So best divider is also it's a much more complex than the multiplier, right? So we can use the SRT division. So it's out of scope of this course, okay? But if you are interested, then you can search for the SRT division, okay? So RISC-V support the division instruction like div and rem. Rem just to create the remainder, okay? So for the signed division, we can just use the div. It just create the quotient and then remainder. So we can get the remainder of division. And then for the unsigned number, we can just use the div u or remu. Okay. So and then this is so I briefly explained about the arithmetic units. So and then these arithmetic units are integer arithmetic units, right? And then also, which means these instructions are integer arithmetic instructions, right? And then, as I mentioned in the previous class, now we will learn about the floating point. So what is the floating point? So like the 1.2. So this is the real number, right? So you know, 0 and positive integer. So it's a natural number, and then the negative integer. These are integer, and then in the integer, so actually the it's so actually integer just to represent some kind of count of some object, right? But we can also use the real numbers in our real life, right? Like 1.2, and then these numbers are called a floating point number. Okay, but actually in the real world applications, we frequently use a floating point number. So let's learn represent how to represent the floating point number in a computer system. Okay. So floating number is a non-integer number, right? It's a real number, but the integer numbers are just excluded, right? So it's a non-integer numbers. So and then we use these floating point numbers for representing very small numbers or very large numbers, like right, like or some numbers like 1.2, right? So then how can you represent the floating point number in decimal number system? Like we can use the 1.2, right? And then multiply by 10 to the power of some number, right? So this is the scientific form of the floating point number in a decimal number system, right? So these floating point numbers can be normalized or not normalized. So this is the example. If this part, this digit just, so actually the left side of this point, dot, then if there is only one digit, then we can say that this number is normalized. So like 1.2 multiplied 10 to the power of 2. And then this is the exponent, right? So we can say that this is a normalized number. But how about these numbers? These numbers are not normalized because for this number start from, you start with 0 point blah, blah, blah. So this is not normalized. If we want to normalize this number, then this number needs to start from 2.000 and multiply 10 to the power of 6, right? How about this number? This number includes multiple digits for the left side of the dot point, okay? So it's not normalized. So we can just represent the floating point number using the normalized form or not normalized form. But in a scientific computing, so we just use the normalized number in order to represent the floating point number. So using the normalized number, then we can represent the all kinds of real numbers, right? It's the same. In the binary form, we can also define a normalized form of a floating point numbers. So this is the normalized form of the floating point number. So we can find the sign plus or minus, obviously. And then in the normalized form, the floating point number in the binary system, it starts with 1. It cannot be 0, and then each digit need to can have only 1 and 0. So, and then in the normalized form, it cannot start with 0, right? So the first number is always 1, and then there are multiple numbers, right? And then this is the binary number. So actually the base is the 2, right? So 2 to the power of some numbers. So in order to represent the floating point number, so what data are required? Firstly, sign plus or minus, and then this data and this data. So this part is called the exponent, and then this part is called the fraction. Okay, so in order to represent the floating point number, we require sign bit, exponent part, and fraction part. Okay, and then in C, you can find the data type float and double. Okay, so float represent the floating point number, and then actually for the float, we use the 32-bit data, and then double is the 64-bit data. Okay, so let's see how we represent the floating point number. So actually, this floating point number is specified in IEEE standard. This one, right? And then there are two different representations, like single precision, it's a 32-bit, so this is the float. And then double precision. Double precision has 64-bit, and so this is double. Okay. And then let's see how to represent the floating point number. Okay. So as I mentioned, we require sign bit and exponent part and then fraction part. So sign bit is 1-bit data because we can just represent the plus and minus, right? Plus is 0 and minus is 1. So only 1 bit is required for the sign bit. And then for the exponent, for the single precision data, exponent part includes the 8-bit data, right? And then for the single precision, the fraction part has the 23-bit data. Double is a different. Exponent has the up to 11 bits, and then double can up to 32-bit data. And then this is the equation, okay? So this is a sign bit. So sign bit just decides the sign of the floating point number, and then the fraction. So fraction is 1.xxxx. So we need to represent these numbers xxxx. So but one is just one, right? So only this part is just stored in the fraction, and then exponent. So exponent is also like 2 to the power of y. So this is the exponent part. But when we store the exponent part, then the exponent part is biased. So actually, the real exponent number is the exponent minus bias. So this bias value is 127 for single precision, and then 1023 for double precision numbers. So you can find that this is the 2 to the power of 8 minus 1, right? This is the 2 to the power of 10 minus 1, right? Oh, no, it's a 7. Sorry, just 7. So instead of 2's complement, so actually the exponent, for the exponent, so use the number from 0 to, so 2 to the power of 8 minus 1, this one. But actually we use the biased number, right? So which means, so actually 0 is equivalent to, no. Exponent 127 is equivalent to 0, okay? Because the bias is 127, okay? So this is the specification. So actually you can just represent the floating point based on the specification, right? So then single precision range. Let's see the single precision range. Exponent 0 and 1111, all zeros and all ones are reserved. It's not used for normal representation. So these exponent numbers, all zeros, 0, and then 1111 are just, those exponent numbers are used for representing special numbers. Okay, so what is the smallest value? Smallest value is the exponent is 0, 1, right? Because 0 are just reserved. So and then actual exponent is the 1 minus bias. Bias is 127 for single precision. So this is number is the 2 to the power of 7 minus 1, right? So it's a minus 126. For the smallest number, the fraction part. So that fraction part is 1.xxxx. So if these numbers are 0, then it's the smallest number. So significant is the 1.0. So this is the smallest number. And then in decimal number, smallest number is similar to the 1.2 multiplied 10 to the power of minus 38. Large number, because all ones are reserved, this is the largest exponent. And then the actual exponent is the 127, right? Because we need to perform the minus bias. And then for the large value, the fractions are all ones, right? So 1.111111. What is this number? This number is equivalent to 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus blah, 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 blah. So what is this number? It's similar to 2, right? Right? It's a high school mathematics. So the largest value is similar to 2.0 multiplied by 2 to the power of 127. And then this is in decimal number, it's equivalent to this number, right? For the double precision, the exponent bits, number of exponent bits is increased. So actual exponent minus 1. Then you can also find the smallest value and then largest value, okay, of this single precision and double precision numbers, okay. And then so what is so actually, so this, floating point number, just we use the binary numbers for representing floating point numbers. What does that mean? Actually, the precision of a floating point number is determined by this fraction part, right? This part. So what is the precision? So precision means that it's the smallest number that can be represented by a number system, right? So for example, if we use the decimal number, so like 1.0000001, right? So this is, so if this number is fixed, then this is the the smallest value that can be represented by the decimal number. So it's the same for this single precision and then double precision numbers. Okay. So single precision is approximately the precision about the single precision is approximately 2 to the power of minus 23. Okay. So because it's a 1.xxxxx, right? And then what's this pin number? It's a 23, right? So the approximately it's a 2 to the minus 23, and then in the decimal number, it's equivalent to 6 decimal digit of a precision, like 1.xxxxxx. Okay. For the double precision, it's a 6 equivalent. The precision of double precision is equivalent to 16 decimal digit of a precision, right? So it's just after the dot or after the point, so actually it is equivalent to 6 digit. So all fraction bits are significant, right? So which means only it's 6 decimal digit, right? And then for the double precision, it's equivalent to 16 decimal digits. Okay, so that's why some precision. All fraction bits are important. Okay, so let's see the example of the floating point. So how can we represent the minus 0.75? So sign bit is minus, so sign is 1. Okay, and then actually the 0.75 is 1.5 divided by 2, right? So actually this number is the 1.1, and then multiply 2 to the power of minus 1, right? So fraction part is so 1.xxxx. So this is the fraction part. So what is the fraction part? Fraction part is 10000, right? Now the exponent. Exponent is minus 1. So this is the exponent, but we need to add the bias. So this one is the 126. So exponent is 1, and then double, for the double precision number, exponent is 1022. Okay, so for the single precision number, we can just represent this number like this. And then for the double precision number, and this number is represented like this. And then floating point example. So what is the number? So we can just split the numbers into sign part, exponent part, and fraction part, right? Sign, exponent, and then fraction. Okay, sign is 1, that means it's a negative number, and then fraction is 0, 1, 0, 0, 0. Okay, exponent is 10001 is a 129. But what is the actual exponent? 129 divided by bias. So this is very important. Okay. So it's 2. Bias is a 127, because, right? So it's a minus 1 multiplied by 1.25 multiplied to the power of 2. So this is the decimal number, right? Understand? And then I mentioned that, so if the exponent numbers is all zeros, or if the exponent number is all ones, and then these numbers are reserved for representing special number. And then these special numbers are called denormal numbers, right? Denormal. It's not normal, right? So if the exponent, all exponent are 0, then this, and then it is used for representing very small number. So it means minus 1. So sign bit is the same, but this 1 is changed to 0. So for the normal number, this number is 1, right? But if the all exponents are zeros, then this is a 0, and then this is a fraction, and then it's the minus bias plus 1. Okay. So if the all exponents are 0, so you can find that this number is very close to 0, right? Very close to 0. But what's the problem about normal normal number representation? So it's the 1 plus fraction multiplied 2, and then minus bias. So this is a very small number, but it is not 0. It cannot be 0. It's a very small number, but because with this one, it cannot be 0. So the problem is that using the normal number representation of the floating point number, we cannot represent 0, right? So if the exponents are all zeros, then this one changes to 0, and then this is becomes the minus bias plus 1. Okay, then we can represent the 0. So, right, if the all fraction are 0, and then if this number becomes what, 0, then it's 0. So you can remember that actually all exponents are 0, then we use these numbers, is the denominator numbers, for representing very small number. So very small number represented the numbers close to 0, right? Then we can also represent the 0, right? And then infinite and not a number. So not a number is it cannot be represented using numbers, right? So exponent is all one, and then fraction part is 0. Then this means the infinity, right? So CPU or RISC-V use this special case for representing infinity, like infinity, right? Plus infinity or minus infinity. So exponents are all ones, and the fraction bits are not 0, then it represents the not a number. Okay, so it indicates the illegal or undefined result. So for example, 0 divided by 0. Okay. Okay. And then, so let's see how to perform the floating point arithmetic. So, and then actually this is same. Okay. So for the decimal number systems, so we can also perform the floating point arithmetics, like floating point add and the floating point multiplication, right? So this is the example, like 9.999 multiplied 10 to the power 9, blah, blah, blah. So how can we perform addition, floating point addition in decimal number system? Firstly, align decimal points, right? So which means we cannot directly add these numbers, right? Because why? Exponent parts are different, right? So we cannot add directly. So she puts numbers with a smaller exponent, right? This one, and then add significant, okay? So number becomes like this. So we need to normalize then, okay? So because this number becomes 10.015, but we can find that this number is not normalized. So we need to normalize and then round up or round down if necessary. So these are floating point addition, the flow of floating point addition in a decimal number system. For the for the binary number, same, right? Firstly, align binary point, okay? So which means that we need to adjust the exponent, and then we just make the exponent the same for the two numbers, okay? And then add the significant, normalize the result, and then check for our over and underflow, okay? And then round up or round down. So it's exactly the same, right? The, the, the flow of calculation is exactly the same. So, but we can find that in order to perform the floating point addition, it's more complex than integer addition, because for the floating point addition, we need to perform these 4 steps, okay? So FP adder, the floating point adder usually takes several cycles, and then it can be pipelined. So we will learn about the pipeline architecture later. But you can just understand it's the hardware. Hardware is more complex, so it may take several cycles. So this is the example of a floating point adder, right? So as I mentioned, we need to perform the multiple steps for floating point addition, right? So hardware also performs the multiple steps. So and then these multiple steps can be pipelined. After floating point multiplication, for the decimal number, for the multiplication, we can just add exponent, right? But because this is a multiplication, and then multiply significant, and then normalize the result, and then round or renormalized if necessary. And then finally, we just decide the sign. Plus multiply by minus is a minus, and then plus multiply plus is a plus, minus multiply minus is a plus. So we can just easily calculate the sign. So these are steps for floating point multiplication in a decimal number system. Same to the binary number system, right? Add exponent, multiply significant, and then normalize, and then round, and then also sign bit is determined. So floating point multiplier is the complexity of a floating point multiplier is similar to floating point adder. Only this part. So instead of addition, then floating point multiplication also needs multiplier, okay? But the floating, like the floating point addition, the floating point multiplication needs to perform multiple steps, right? So it also usually takes several cycles. So this is how the floating point arithmetic is performed, okay? And then you can just remember that the floating, so actually in this course, we will not cover how to design floating point hardware. So this is also the out of scope of this course. But you can just understand that floating point arithmetic, the hardware complexity is higher than the integer arithmetic unit. So it takes several cycles, okay? And then it can be pipelined, okay? So now, as I mentioned, we will learn about the hardware architecture in chapter 4. So which means you need to understand the complexity of hardware and then some delay. So if we use the more complex hardware, then more complex hardware may exhibit the more, it may require more cycles. Okay. Okay, let's learn about the floating point instructions. So in chapter 2, we learned about the registers, and then I mentioned that these registers are integer registers. So what does that mean? Only integer numbers are stored in integer registers. So for the floating point numbers, in order to handle the floating point numbers, we require separate registers, okay, additional registers. And then these registers are called floating point registers. And then there are 32 floating point registers, like from F0 to F31, okay? Then usually it's a double precision. And then if we use the single precision value, then it just use the lower 32 bits, okay? So what does that mean? The size of a single floating point register is 64 bit, right? And then there are 32 registers, okay? So in order to access the floating point registers, so we need to use the floating point instructions, okay? And then, so for example, the RISC-V supports the floating point load and the floating point store, like FLW, FLD, FSW, and FSD. So these instruction means so FLW, floating point load, and then word. So what does it mean? It just load 4 byte. So it means it's a single precision. Okay, it load single precision number from memory. Okay, FLW. So because the registers are separated, so we need to use the floating point instructions FLW to access the floating point registers. So these are examples of the floating point arithmetic instructions. So actually, in order to represent the single precision and double precision operations, we need to use the postfix, like .s, like this. So it's a postfix for representing single precision, and then the double precision we use the .d. Okay, it's the postfix of the floating point instructions. Okay, and then as you can see, so these instructions start with f. F represents the floating point. So f add .s, which means this is the floating point add for single precision numbers, right? And this is the example. And then branch also has the branch.count, okay? Like this. So this is the example assembly code. So you can find that these instructions use, so this code uses floating point instructions. Okay. So and then actually the IEEE standard defines some additional specifications for floating point, but and then if you are interested, then you can search for this IEEE standard. Okay, and then I will skip the server parallelism, and this is some interesting topics, all right? Policies and peoples. So I mentioned that so we can use the right to shift operations for replacing division, right? So if because we are using uh, a binary number, then we can just replace this division with the right to shift. But when we use the right to shift instruction, then we need to use this instruction with quotient. Okay, so this is the example. So -5 divided by 4. So this is the actually what's the right result? It's -1, right? So but if we use the right to shift operations, then it becomes this one, and then the result becomes -2. So this is the incorrect result. So for the positive numbers, so it's okay. It's okay to use the right to shift for division, right? But when we apply the right to shift instructions for the negative number, then it may generate the incorrect result like this. Okay, and then another another error is the error can be generated by associativity, right? So this problem is caused by the limited resources, the limited representation of the floating point number. So we already know. So in the real world, so x plus y plus z is equal to x, y plus z plus x. So we can firstly calculate the y plus z, right? But in a computer system, because of the 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 representation of floating point numbers, the result can be different. So let's see the example. So x is very large number, and then y is the same number, but only the sign is different, right? And then z is a small number, is a 1, just 1.0. So if we firstly compute the x plus y, then this is 0, and then 0 plus 1 is a 1. How about this? Y plus z, one very large number plus 1. Actually, in a computer, so because of the limitations of precision, limited precision, we cannot actually we cannot represent the -1.0 and then very small number 1 using floating point number system. We cannot represent. So the result becomes this, and then plus no. Result becomes this, and then plus -1.5 large number, it becomes 0. So the result can be different because the floating point number cannot represent the whole range of precisions. Okay, so you need to understand this issue. So sometimes, so when we apply the associativity, then the so when you change the the order of computations, then the final result can be different. Okay, so this is the precision issue. Precision issues of the floating point number. Okay, and then also Intel has so the old CPU, so Intel Pentium had the floating point divide bug. Okay, this is bug is very popular bug. right? So if you are interested, then you can read this article. Okay. So, so in this chapter, we briefly learned about the integer arithmetic units and floating point numbers representation, right? So actually the floating point number representation is an important topic. So you need to understand it, okay? Okay, so I will stop here, and then please be prepared for the midterm exam, and then good luck for the exam, okay? So see you after the exam. Bye, guys.